How do optimization algorithms actually find the single best answer out of infinitely many possible choices? Welcome back to OptiMind. Today, in video 2.2, we are exploring the graphical method, the most intuitive way to visualize and solve a two-variable linear programming problem. While real-world problems often have thousands of variables, solving a 2D problem on a graph reveals the fundamental geometric secrets that power all advanced LP algorithms. Let's walk through a classic example. A furniture factory produces two products, tables and chairs. Each table yields $50 in profit, while each chair yields $30. Our goal is to maximize total profit. However, production is limited by two resources, assembly time and finishing time. Each table requires 2 hours of assembly and 1 hour of finishing. Each chair requires 1 hour of assembly and 1 hour of finishing. In total, we only have 40 hours of assembly and 30 hours of finishing available per week. Step 1. Plot the constraints. We draw our axes, x1 for tables and x2 for chairs. Since we cannot make negative furniture, we stay in the first quadrant. Next, we draw the constraint lines for assembly and finishing time. The area that satisfies all constraints simultaneously is called the feasible region. Any point inside this shape is a valid production plan. Step 2. Find the corner points. Notice the geometric shape of the feasible region. It is a convex polygon with specific intersection points, called extreme points or corner points. Step 3. Evaluate the objective function. Here is the magic of linear programming. The optimal solution is always located at one of these extreme corner points. We simply calculate the profit at each corner point. The origin, 0, 0, gives 0 profit. Producing only tables or only chairs gives moderate profit. But the intersection point where assembly and finishing capacities are fully utilized yields the maximum profit of $1,100. This fundamental principle is known as the fundamental theorem of linear programming. What happens when a problem has no solution or infinitely many solutions? In video 2.3, we will explore special cases in LP, including unboundedness, infeasibility, and multiple optimal solutions. If you found this visual guide helpful, smash the like button, subscribe to OptiMind, and drop a comment below. Did solving LP geometrically make the concept clearer for you? See you in video 2.3.